Gnanam paramam dheyam. Knowledge is supreme.
Okay, so today I thought a quick questions which one can ask for other coupled potential energies. Okay, so the couple of them is you can have two coupled harmonic oscillators, you can have a harmonic oscillator in the presence of an electric field, you could have a particle which is oscillating in a harmonic oscillator potential and is also subjected to a magnetic field. So these are some of these things where your already learned tools of harmonic oscillator will actually help you to use that data and solve them. You don't need to redo these calculations. So these are the simple tricks which you can employ and get results directly. Okay. So suppose I had given you a potential energy which is x plus y the whole square. You can take it to be motion in 2 dimension. Suppose I have a potential energy which is x plus y the whole square. Can you solve the Schrodinger equation? How will you solve it? You can try to rotate your axis, coordinate axis, make 45-degree rotation such that there is a potential in one of that direction and zero potential in the other direction, and you can solve this. Okay, so this is a trick of making a suitable coordinate choice which helps you. This we have done many times, right? We do take a suitable coordinate choice depending on the situation. So simple trick involves change coordinate system, write capital X as x plus y, and then write the other coordinate which is orthogonal to this coordinate. So if this is rotated by 45 degrees clockwise, this has to be rotated 45 degrees. You know what I mean. When you clockwise, then the two orthogonal coordinates have to be of this type. Then what do? Write the Schrodinger equation in 2 dimension. Instead of using small x and small y, rewrite it in terms of capital X and capital Y. I am sure you have done all these change of variables many times in your JEE and your math course. So in this capital X, capital Y, the coordinate change if you do in your Schrodinger equation, this will be your Schrodinger equation. With the potential, this one will have a half x square. You can still treat it to be a one-dimensional problem, but then if the motion is in 2 dimension, it behaves like a free particle in the other direction, so you have to keep track of that. So in this coordinate, the potential energy is only a function of x, and we can use separable functions, psi of x and psi of y, exactly like what you did in your. So use this separable functions, just a standard one I was telling you in 2-dimensional harmonic oscillator or 2-dimensional particle in a box, and then as he already pointed it out, psi of x will behave like a solution to a harmonic oscillator with spring constant, let us say k equal to 1, and psi of y is like a free particle. So when you write the wave function, like suppose I want to write the ground state wave function, let us say, ground state in the capital X coordinate and a free particle with some momentum in the capital Y. How will you write this wave function solution, someone? So let me call this as psi of x capital Y to be psi of x, psi of capital X capital Y, and psi of capital X, let us say for the ground state, will be proportional to e to the power of, let me not write those constants, x squared, some constant numbers, and psi of y will be proportional to e to the power of minus I kx, sorry ky e to the power of minus I k capital Y. What will be the energy now? Energy for this case n equal to 0 and a specific k, half h cross omega for the y piece, and then h cross squared k squared over 2m or 2m, right? Is that clear? Energy is also sum up over the x coordinate energy. In the earlier case, in the two dimensional harmonic oscillator, you had nx plus half h cross omega plus ny plus half h cross omega. But here the capital X is like the harmonic oscillator. I am specifically taking the ground state. So it will be half h cross omega for the capital X coordinate, and capital Y coordinate it will be like a free particle. So I didn't do the calculations here. I assume the harmonic oscillator solution. Looking at this given potential, I chose a different coordinate system where it behaves like harmonic oscillator in the capital X coordinate and free particle in the capital Y coordinate. Okay, so this is why it is coupled. X plus y the whole squared is coupled. After you have got this wave function, you could go back and write capital X and capital Y in terms of small x and small y, and you can get it in your original coordinate system, but the energy spectrum will not change. Energy is an eigenvalue, that will not change. You can go back and write this wave function in terms of, you can replace this by x plus y by root 2, and this one is x minus y by root 2, and then you can get back your wave function in the little x little y coordinate. This is a small trick. Okay, so now let's take the particle in a constant electric field. Okay, so let's take the particle in a harmonic oscillator potential to be subjected to an external electric field. So when you want to put the potential energy, let's take it to be in one dimension, you have to add a E is the electric field. Don't confuse this with energy. E is the electric field, E times x, as q is the charge of the particle. How will you solve this? So you try to see whether you can redefine again another coordinate such that it can become your familiar potential. So you complete the squares to attempt such problems. How do I do this? If you have x squared plus ax, so it's same as shifting your x and then subtracting a constant. Shift your x and subtract the constant. Then what do we have to do? We make a change of coordinate. Instead of x, you call a new coordinate x prime, which is a shifted coordinate. Take a shifted coordinate. Then what happens to your system? Your potential energy, which was this, becomes shifted. This A, which I wrote as a compact notation, is actually to be seen from this picture, how you change your coordinate, and there is a 0 of the potential energy is shifted. That's just a constant. What will be the energy eigenvalues for this system? What will be the ground state energy? Half h cross omega minus the constant shift in that energy, which is q squared e squared by 4k squared. What happens to the wave function? Wave function will have a peak earlier at x equal to 0 in the absence of electric field. In the presence of electric field, it will get shifted. It will be shifted by the QE by 2. Do you need to work out the solution? No need. If you know the harmonic oscillator solution, you can say for this potential, you can do this trick of completing the squares, and then you can read off that the wave function will get shifted. The peaks of the wave function, wherever it was, it will shift by, or the whole wave function is shifted actually. But the energy eigenvalues don't change. I am just asking that if you take the stationary state solutions, I am just looking at the time independent solution, the solution will look like the same wave function plot but shifted to x. Is that fine? That phase factor, time evolution phase factor is there for all problems. So if I ask you, giving you this problem and ask what is the first excited state energy, I will see all of you doing 10 pages of calculation in the mid-sem. Don't do it. Just have to write a line that this is the trick. Assuming harmonic oscillator solution, it's 3 by 2 h cross omega minus q square e squared by 4k square. This is all you have to write. Use the power of many of these, simple tricks before you go into doing rigorous calculations. So no need to do a calculation. Okay, so I have just said here the solution will be shifted by that x prime coordinate, and you can rewrite it in terms of, if you remember your earlier coordinate how I wrote the rows, you can rewrite it and you can say that the energies are n plus half h cross omega for the excited states, but it is shifted by a overall, every energy level is shifted by q squared e squared by 4k squared in the negative direction. Okay. So classical mechanics and looking at Lorentz force, I am assuming you all know. So Lorentz force, suppose you want to look at charged particle in the presence of a magnetic field along the z direction. This is the most general Lorentz force, which includes electric field and the magnetic field, but I can try to look at what is the force when you apply magnetic field along z direction, and B can be written as curl of vector potential. So we are going to look at absence of electric field. What we will do is, naively, we will replace the momentum in classical mechanics. This is what we do in classical mechanics. We replace the momentum by a shift. The reason why we do this is, if we take the Lagrangian with this shift and write the Euler-Lagrange equations, you will get back your Lorentz force. Okay, I am sure classical mechanics course you would have done this. If you have not done it, right now you take this as a data. Some point you have to write the Euler-Lagrange equation for the shifted, and you can show that you get the Lorentz force. Just to give you a flavor, see, for a free particle you want mx double dot to be equal to 0. How do you do this in classical mechanics? You take this to be half m x dot squared, and then you have the principle of least action, extremizing the action, which is L dt, delta s equal to 0 will give you del L by del x dot d by dt minus, or this is del L by del x. If you try to substitute here for this Lagrangian which is given, you will end up getting del by del x dot will give you 2m x dot, and d by dt will give you, the half is already there, so it's mx double dot, and del L by del x for this is 0, so that's why you get this equation of motion. Similarly, for a particle in, so similarly you can do for a particle in a magnetic field. So you can try to write your Lagrangian as, you will have a term where you can try to rewrite it in terms of x dot squared. So you can basically Lagrangian is not the right one when you have to write the momentum, it will become the Hamiltonian. How is Hamiltonian related to Lagrangian? Q p dot or q dot? Yeah, this is the Legendre transform, which will give you a function of x and p, and this is a function of x and x dot, and you can write what is the Hamiltonian and look at the equations of motion there also. So what I am saying is that for the particle in a magnetic field, if you replace p by p minus Ea by c, the whole squared by 2m, the free particle, and if you try to rewrite your either the Euler-Lagrange equation using the above or the Hamilton's equation and convert it into second order differential equation, you will end up getting a force which is the Lorentz force. Okay, this I will leave it to you to check. Fine. So, in the absence of electric field, you can make a shifting to make contact with the Lorentz force, and let us take a specific choice for the vector potential. This is just in our hands. Why it is in our hands? You can try to get the same electric field and magnetic field but different A's which are related by gauge transformation, right? You can choose another choice, another A such that the curl A will give you the same magnetic field and similarly the corresponding electric field if you want to find. So, this is one choice. This is one choice which will give me the magnetic field along the z direction. So, force law, which is dp prime by dt, this is what I was saying, and you can write the Hamiltonian with this choice of A. This is one specific choice. I get this as the Hamiltonian. Now, look at this Hamiltonian and tell me what is happening. Yeah, so let us just keep the C to be 1 just for, you can put the C also, but let us just, many times what we do is we put M equal to 1, C equal to 1, so maybe I mechanically put it, which is not right. Okay, but look at this Hamiltonian. I substituted P prime as P minus EA by C, and the capital A, the vector potential vector, I am choosing the AX component to be minus BY. So, there should be a by C as he was pointing it out. Let us just shift it with putting C equal to 1. So, there is a BY shift here on the PX. Incidentally, is this correct? This gives you magnetic field along the Z direction. Curl of A, if you do, you should get BZ to be B. How do we separate the wave functions? Definitely the Z coordinate is like a free particle. X and Y is coupled. Why? There is a Y term here and a PY term here, and there is also a cross term PX with Y. So, you cannot separate the XY wave function, but you can separate the Z wave function. So, first of all, you have to stare at the differential equation and see how to first get a feel of how to write the solution. Then you can also make trial functions. You can start trying various trial functions for the coupled XY components and see if I plug in and I compare powers of X, compare powers of Y, if I get consistent solution, then that is also a solution. This is what you have done in your earlier course. You are given a trial function and you compare the powers of X and find what is the energy eigenvalue. So, that also can be done. But before we do that, let us just stare at it and see how to separate the wave functions. And we know that, so we see that the Hamiltonian operator can be separated as a coupled one with X and Y coordinates and the Hamiltonian for the Z, which is just this Pz squared over 2L, which means I can write psi of XYZ as phi of Z times eta of X. So, separation of variables and you have E minus E. Have we solved the problem? Not yet. Why not yet? I need to find what is the total E. I need to find what is E1. I need to find what is eta of XY. Phi of Z I know. Why phi of Z I know? It is just a free particle equation. We have been doing this even in the one dimensional step potential everything. So, solution to the Z is a free particle. I am putting a K subscript Z, where K subscript Z is root of 2m E minus E1 by H cross. Okay, so now comes, we have no way in which we could try and fix eta of XY. We tried to look at a trial solution. Okay, so this is just a trial solution. This is not a derivation. We want to just plug this solution into this equation and see what we get. No harm in doing that. Only thing you can see here is that I pretend as if there is a free particle in the x direction, but then the y component is dictated by this kx in some fashion. It is not separate actually. This f of y was not independent of this. There is a kx here which shows up here. So, this is the way I am trying to look for a plausible solution to this equation or take it to be a trial solution, and we will plug it to the above equation. So, let us plug in this and write out the top equation. Can you plug it in and check whether you get this? So there will be a px squared. Px squared will give you a kx squared because you will have a del by del x. Minus IH cross del by del x will give you a kx. So substitute this and check whether you get this. I've written it for some selfish reason in this fashion. Looks like a harmonic oscillator, shifted harmonic oscillator. But the shift is dependent on the magnetic field and the kx, which is the x component wave function. This is just a completely different, this is not, this if I had not given to you, you will not be able to reach this. But if suppose I give you this trial function, we will do by a different method where we will get this feel also. I just want you to get a feel of, if you are given potential energies of different types, knowing the harmonic oscillator, can you attempt some of these problems without trying to rigorously try and solve the differential equation. That is the main aim. So, because I have given this form, and if you plug it in, you will see that the operator, differential operator which you have here, or the Hamiltonian operator, these two sides are eigenfunctions, exactly like your time independent theories. But you can read off from here that there is a frequency, omega squared is EB by m, EB by m the whole squared is omega squared, and it is a shifted oscillator with the shift y naught dependent on the x component quantum number kx and the magnetic field inversely proportional to the magnetic field. So, what will be the solution now? We can try to write what is f kx of y. Now, you also see that kx dependence is showing up where the peak or the wave function shift will happen. If kx is 0, it will look like your usual harmonic oscillator in the y coordinate. If kx is non-zero, if it is positive, it will be shifted in the positive y axis. If it is negative, it will be shifted in the negative y axis. Is the picture clear? This step, please work it out. Just substitute this one into this equation and verify that this is there. Okay. If you have not already done, please fill it up. So again, it's a shifted oscillator, and the frequency of the oscillator is also dictated by the given equation, which is EB by m. Clear? So what will be the energy? Half h cross omega will be EB by m for the ground state, and other states is n plus half h cross omega. Omega is EB by m. So finally we see that we can actually find the solution like this, e to the I kx x, and then fn with the shifted y to y prime, and appropriately you could write it in terms of the new coordinate by putting that m omega by h cross. Eigenvalue will be, this will have n plus half h cross omega, where omega is EB by m. Is that the energy or something more is there? The z coordinate energy should be added to this. Yes. So the total solution in 3 dimension for a particle subjected to a magnetic field, we can try to use an appropriate choice for the vector potential. Magnetic field is along the z direction. We can make an appropriate choice for the vector potential and try to give an ansatz for the separable function. E to the I k z, z is separated, but then x and y are connected. Okay, so this y prime is actually a function of kx. It's a function of kx. So this is the total solution. The quantum numbers are not only n, you also have a kx and a kz, and the corresponding energy n the energy for an nth excited state in the y coordinate, but it can have a kx which is contributing to the energy in the x coordinate in general and kz, but we have seen that the kx and n are coupled in such a way that the energy depends only on the harmonic oscillator, kind of shifted harmonic oscillator. So there is no kx dependent energy. It's clear? Kx will only show up in the shifting of the harmonic oscillator. The harmonic oscillator gets shifted by coordinate y to y prime, where y prime is dependent on kx, but the energy does not get contribution because there are only two equations, the E1 and the E minus E1. E1 was n plus half h cross omega, E minus E1 was h cross squared kz squared over 12. There is no kx. So what does this tell you? There is a degeneracy. Kx can be anything for a given n and a given kz, which means there is a infinite fold degeneracy in the wave functions. You can have many possible wave functions for different kx, but a specific n and a kz. Highly degenerate, infinitely degenerate. Okay, pictorially I can show, if I look at the ground state n equal to 0 with a specific kz, I have put it, I am not very good at putting infinite, nobody is good at it. So I just put in many lines to say that each level you can have many wave functions depending on choice of kx to be different, but all of them will share the same image. Okay, so this is what is the called as sometimes as Landau levels. So I have taken you through a small tour where I took the coupled harmonic oscillator. I said you can undo it by appropriately rotating your axis. Then I added for the 1D oscillator an electric field, and we had a trick of completing the squares where it becomes like a shifted harmonic oscillator. Then I went to a little more complex problem where I added a particle in the magnetic field which should satisfy Lorentz force, which will give you a Hamiltonian, and with a suitable choice of the vector potential you can end up getting the wave functions to be highly degenerate for a specific n and specific kz. Kx can be anything.